version, yeah? So we end up having this wn plus 1 equal, yes, and then we said let's say b equals 0, yes, so initial conditions um, 0 with 0 or Dirichlet.
Or?
Yeah, Dirichlet.
What's
Dirichlet. It's the name. Like if you have Dirichlet initial conditions, it means that the point at x equals 0 and x equals L are 0.
Could you write it extra?
Dirichlet. D. Just a name, and it basically means that the conditions are 0.
Same.
Yeah, 0 or Dirichlet. It's the same.
Boundary and condition 0.
Yeah. Okay. So
this is the matrix version.
yeah, we're here.
This one.
Yeah. But we already did this, but we need
We have a
also
condition
this
of
to
zero.
understand what we did
Zero,
today.
This one last week.
Yeah. Okay, so just like a
exactly.
review. Okay. And we want this, of course, like to converge. Yes, not to just go away to infinity. So what we want, because now we have basically we want the eigenvalues of S to be smaller or equal than 1. Yes, in absolute value. Yes, because then, sorry, because this is there's an N here. Yes, so, like this, and the solution basically was n bar equals Sn W0. Yes. So we want the eigenvalues of S to be smaller than 1, so this converges as n goes to infinity. Yes. Okay. And
What's called this? It's line or?
This absolute
Absolute
value.
epsilon.
Yes.
Okay.
Okay, so of course, like if lambda is positive, blah blah blah. So we want lambda to be smaller or equal than 1. Yes? That's basically this. And because S is 3 diagonal, or 3 diagonal. Let's try diagonal because there's like zeros up and down. Then the eigenvalues are this form: 1 minus 4r sine square of S into delta x. Yes. You just like you can solve, and I'm trying to write this the solution of this nicely. When I have it, I'll send it to you.
Okay, that's all.
Yes. Because there's no, like it says, like you can derive nice formula, but it doesn't say how. Okay, so these are the lambdas, and of course you want lambda to be smaller or equal than 1, so you have 1 minus lambda s minus
What's this?
minus 1,
Minus.
because you want the absolute value to be smaller or equal than 1. Yes. So this is true because you have 1 minus something, so 1 minus something is going to be always smaller or equal than 1. Yes.
1 minus something, yes.
Yeah.
For sign or just for any function?
Like if you have 1 and you take something from 1, this is going to be smaller than 1.
Yeah.
Don't just this is like, it is trivial. And then the second part, if you do it, here are the equations, you end up by having that r has to be smaller or equal than half. Yes, you can look at the operations here, it's not difficult, and you can just keep this. So if r is smaller or equal than a half, then our solution converges. Yes, so it's good. If not, then it's not. Yeah, and this is the magic version of of the forward in time, central in space. Yes? So one problem about this, one problem about this is that S, yeah, can be as big as you want. Yes. So in this example, the stability basically involves finding all the eigenvalues of S, and if S is really big, then it gets complicated. And the condition that lambda, either absolute value of lambda is smaller or equal to 1, only guarantees, in this case, our stability, because we have our equation is parabolic. But for hyperbolics, we will see that this method of looking if it converges or not converges doesn't work with the hyperbolics. So like this method is just good for in this case, but not for in general.
For hyperbolic, it's greater than 1 hyperbolic.
Like in this case, we can, like in this case, the hyperbolic ends up being like this case. In this case, we can solve it and see it. Yes, but with the parabolic, we are not going to end up with this formula. So, looking at the eigenvalues, it's not going to be useful in the hyperbolic case. So we need another method to test the convergency. Yes, and the other method is the called Fourier
Infinite numerical.
or von Neumann. Method.
This is a new method now.
Yes.
New method to solve.
No, to test the convergency. Yes, because here we did alright, so we
Local
let me check, I have the okay, so what we did is we look at the local error and we looked at the stability. Yes, so now we need to look at the convergency. Yes, and that's what we're testing, if it's convergent or not convergent. Yes, this matrix version of this, by changing the FTC scheme to a matrix version, it gives us one way to know if if our approximation converges or not. But this method is not always going to be useful. So we need another method for other times where this one is not useful. Yeah? So here we start that we have ut equals to uxx, and with alpha and beta 0, like because it's Dirichlet conditions, and the initial condition, so
0 as well.
at x 0, this is called f. Yes, this is our system.
And from here, this should be 0. In this
No,
method.
this is initial condition, and this is bound. No, sorry.
No,
it's
this boundary.
Sorry, so this is initial, no, boundary. Sorry. Yeah. This boundary condition and this
This
initial
initial
condition.
condition.
Yeah, sorry. Okay.
This is the like a condition. Should be 0.
No, these are because these are our boundary condition. Yeah, we say okay. In our case, we want
Okay.
the boundary condition to be always 0. Yes,
Okay.
and you can test that if you take xt to be equal a the exponential minus pi t square sine of pi x, this is a solution. You can, if you take
Equation.
this
Derivative.
over time, it gives you minus pi square, and then the same, yeah, u. Yeah.
Okay, yeah.
Then
Come,
if you derive twice
I guess.
over time, it gives
Cool.
you the sine, it gives you cosine
Mine.
and then
Square.
sine, but with
Delta
the
Mine.
sine. So yes.
Yeah.
So it's the sine, and then pi goes out twice,
Twice.
and
Square.
then this stays the same. So this holds. Yeah.
It's exact. This for exact.
This is like the solution, and if
Exact.
you put t
Approximate.
yeah, if you put x equals 0, yes, or x equals 1, this is going to give you 0, so it's the boundary conditions, yes. And at t equals 0, this gives you a sine of pi x, which is these initial conditions, yeah. Okay, so this is a formula, and this is a solution.
Let us solution.
Can I take this?
Yeah. It's for mine.
Okay.
I'm dark معانا.
And because this is a linear,
It's just
this is linear,
this is the first one.
so because our differential equation is a linear one, yes, because it doesn't have u multiplied by u.
Two variable. I mean,
No,
no, two variable.
Linear, it means that this ux, ut, is going to be non-linear,
Okay.
yes, but our case is linear.
Yeah, I
So
get it.
because if our case is linear, then
And one
See-
dimension. I mean, it's
Sorry?
one order for first order,
second order.
second order because
of-
XX. Yeah.
Yes.
Okay.
Okay. So because our differential equation is linear, yes, and we have this solution, then we can have a more general solution depending of k, which is going to be ak e to the minus pi square k square t sine of p k x. Just try to do again differentiate respect of time. This give you minus pi square k square, yeah, and again solution. And if you differentiate twice respect on x,
Yes.
it gives you this twice with a minus, and again the same solution. Yeah, so this is another solution of our formula. Yes. So if you just sum,
Excuse me, what's mean
Yes.
k here? Like
k is just a
Number of-
number. Yes, a
number of derivative?
No, look, this k. So if you want, it just here.
Yeah, here without k. It's same
Yes,
this equation.
it's an equation but with a k, because it depends. K can be 0, 1, 2, 3, 4, 5, 6, 7.
Okay, what's mean if k equal to?
That where is k, I'm going to put a number 2.
Only just
That's
number.
it.
You mean here?
Yes.
Doesn't mean anything about derivative
Nothing.
or something
No, no,
like
no,
that.
no. So k is a natural number.
Mhm.
Yes. Okay. So
Yeah, but if zero will be different. If zero here.
if this is 0, this is 0.
Yeah.
So
Condition.
the solution is 0,
Yeah.
and the solution 0 satisfies this.
Yeah.
So it's a solution.
Mm.
Yes, it doesn't matter. And you can always start at like n equals 1 or n equals 0. wherever.
Natural.
Like I don't know. With some people
Start with one.
natural,
Start with one.
and if
From one,
not,
yeah.
But no, some country start with zero.
yeah.
Some
Like I know
this-
that sometimes if you put this and start, it means that start with 1 or with I don't know.
كيف
Yeah, no, I think
With this-
include zero, I think.
Well, it's depending of the countries and
of the country or the
Yeah.
so
Science.
because every one of these is going to be a solution, yeah, I can have my general solution to be the sum from 1
To n.
to j here, yeah,
خلصنا.
ak
خلاص.
a minus
الطبع الثاني.
This is the general
this is the general condition. Yes?
Yeah.
Mhm.
Because we've seen that this is a solution. A more general one is this one. And because it holds for all k, we can just sum them.
Mhm.
Because it's linear, we can just,
Mhm.
yeah? So we can see that this is a general solution. Okay. Just notice that the sign of pi kx,
بعدين نشيل نضيف.
this is basically, you can write the sign in terms of the exponential, saying I pi kx minus e I pi kx divided by 2. You can write this
Like this.
yes. Is a
It's for approximate, yeah.
because e to the what is it? E to the z, yes, a z being a complex number,
Sorry, this is to get sign, right?
yes, this is e to the z is basically this number, e to the z, yes, so e to the z, it gives you cosine of x, and then because this and I was thinking there's a plus sign of z, if I'm not I have to rename this. Well, you can check, there's a formula online, but you can, if you, sorry, like this, no,
What's this? Sorry.
z,
This is it. Okay.
complex number. So
Okay.
in our case, yes, e pi kx, yes, this gives you cosine of pi kx plus I sine pi kx, yes, and then we have e to the minus I pi kx, this is going to be equal cosine of minus pi kx plus I sine of minus pi kx, yes, and this the cosine of the negative
Would be here.
let me check.
One
Because this
go off,
minus, so
one
it's going
go
to be
back,
it's
like
going to
that.
be this
Mhm.
one, because here you sum, here
ما
is.
له داعي.
Yeah.
So the cosine is going to remain the same. Yes, this number
Mhm.
remains the same. So this is basically cos of pi kx, but the cosine, we have it here. Now we have it here, so it's going to be minus. So this is minus I sine of. Sorry, this is on I here. Pi kx, yes. And now if you just minus,
I get this.
yes, we take cosine minus cosine goes away, and this minus this, this gets 2i sine, yes, and divided by 2i, it gives you this. Yeah.
Mhm.
So because of this,
Yeah.
okay. So because we have this, yeah, we can just substitute this into here. Yes, and then we have the sum of k equals 1 to j ak e to the minus pi square k square t, and then multiplied by e to the
Pi.
I pi kx minus I minus I pi kx over 2i, yes?
Mm.
And then in our case we have k running from 1 to j, yes? And if you see, we're going to have ak over 2I, and then e to the minus k squared t e to the a b k x, and then we can put just a minus the sum of k equals 1 to j of a k over 2I minus pi squared k squared t, and e to the minus I pi x k. Yes? So if we change this k, yes, when k is equal 1, this can be seen as minus 1. Yes? When k is equal 1, this is going to be minus 1.
Yes.
Yes? And when k is equals k, j is going to be
-2.
minus j.
Okay.
Yes? So we've seen that our k runs from 1 to j here, and here, if we take this minus go with k, it goes from -1 to minus j. Yes? So instead of having like two sums, we're going to have the sum from k equals minus j till j. Yes? And then some constant, and then e to the minus p k squared t e to the e pi kx. And this
No,
constant I'm going
this-
to tell you now.
This we are here. We are here.
Yes. So this is going to be the same.
Mm-hmm.
Yes? Because it goes from 1 to j.
Equal here.
Yes? And because now the sum goes also from minus j. Now it go here it was going from 1,
Yeah.
and now it's going from minus j, so we are taking into account this number. Yes?
Okay.
And the thing is that from k to 1 till j, ck is just going to be ak over 2I, and from minus j till minus 1, ck is going to be minus ak over 2I, in order to have this.
Yes.
Yes? It's basically like a short notation. And if we say, oh, but here k goes to 0 as well, and here we didn't have k equals 0. But if we put k equals 0 here, yes, at k equals 0, here, if we put k equals 0, yes,
Yes.
this is 1 and this is 1, so basically this is 0. Yes, so at k equals 0, this is 0, so we're not adding new extra term or anything. Yeah?
Yes. Yes.
Okay.
Okay. It's theorem, yes.
Let's say again. In this equation, this like from his head, bring this to satisfy this
Yes,
one.
like this is a solution of this.
this solution of this.
And you can check
All
it.
the
We checked.
equation. Yeah.
This is like example, right?
No, not example. It's
Theorem.
okay. After that, he study this equation.
Yes.
Realize this equation here.
Yeah.
Till achieve this one.
Yes.
Achieve here. This
Actually
one.
one. Yes, we have this equation, and this for every k is a solution. So okay, so if for every k is a solution, we're going to sum them, and we know that because the differential equation is linear, the sum of solutions is a solution.
Yes.
And then this, another way to write this thing is this way.
You
Yes.
write with some linear equal sum because
لا
مرة
بس
here ولا green طيب green.
Green. Okay.
This
okay. So we because our PDE is linear, comma, if u
دقيقة نسوي كذا.
if u and v are solutions, then u plus b is a solution.
Here.
And because for
Yeah.
every k the solution, the sum
Yeah.
of all of them is solution.
The sum of solution is solution.
بس مكان هي.
Yep. Okay, so like you don't have to really remember everything.
Yeah.
You can. We're going to just
Use the.
that this
yeah,
it
this
can also be written this form. Like if you can understand like how we get
Yeah,
it,
it's like
good.
algebra. We need
Yeah, but it's
see it again.
it's not like okay, I'm going to memorize this because you don't have to.
It's not important to
Ah.
proof.
Okay.
هذا حق.
Okay. So now, because we have xjtn, yes, this is basically going to be j times delta x and n times delta t. Yes, and our here. Now we're going to just look at this bit, yeah? So at this bit, yes, what we have is if you, instead of t, we have n delta t, and instead of x, we have j delta x, yeah? We just have e to the minus pi.
Excuse me.
Okay. Yes.
If j equals 0, this will be 0, isn't it?
No, this is going to be 0, but this depends on the time.
If n and j equals 0, this will be 0, 0.
Yeah,
And
because
start
it's
from
an initial condition.
start from 0 and 0, 0.00.
But this, remember that this is our grid,
Yeah.
yes? Because
Yeah,
again,
jumping like 0, 1, 2, 3,
Yeah.
Yeah.
like then, yeah.
mhm.
Color, what is you here? No.
No, this is a point.
Point.
Yes,
That's the point.
it's a point. Because remember, because we're doing numerical, so we cannot solve this explicitly. We're going to do it like numerically. So we need this algebraically, and now our u, we cannot solve our u for every point, but we can solve it for every
Point.
point in the grid, not in the real line. Yes. So if we just like solve this into, we have m delta t and e to the r pi k j x. Yes, this is what we have from here. I'm going to put this and say triangle. Yep. Okay. So because if you take a number like x a b, this is the same as x a to the power of b. Yes. So what we can do here is to e to the minus pi squared k squared.
شو نعرفه من هذا؟
لا هذه دلتا.
Or if you want, you can
يزمد
put-
كذا.
Go like 2 stars.
كويس جزاك الله خير.
Okay, so we're just going to put the same, but now I'm going to put this n. Yes? And now I'm just going to copy this the same k, j, x. Yes, everything is okay?
Yeah.
Just written the same thing, because this is just multiplying this, and you get this. Yep?
You get this from this or?
No, this doesn't change.
Yeah, boy.
But this, instead of putting the n with all the others, I'm just
outside.
going to put it outside.
Like
It's going to be the same.
Yeah, like this.
Yes. And now I'm going to call this psi.
So this is our row.
No, this.
Yeah, this one. Okay.
Yes. And this I'm just going to put I pi k j x. Yes.
Okay,
Not
go ahead.
changing anything.
Nothing.
Okay. So this is so we can have here where- okay, so now we say okay,
Go.
let's denote this as w j
Actually,
n. Yes, our approximation. Let's say, okay, you are going to approximate our solution, yes, on this bit. Yes. Again, like here, like we're kind of forgetting this, yes, and just being again with this, yes, not just a sum, just one solution, yet, because if we know that one is solution, then we can sum the other ones. But just going to look at this, and again, what we wanted, yes, in the matricial form, because we had this. We wanted that the eigenvalues of S were smaller than 1. So now, in this case, what we want is that W, this is going to be smaller or equal than 1. Yes?
Smaller than 1.
Because here, what we wanted here is Wn smaller than 1. Like above, like the vector 1. Yes, but we need from this, because Wn is equal to this, basically we wanted this to be smaller than 1. Yes? So in this case, again, we want this, but because we chose this to be our approximation, this implies that the absolute value of a k, j, x becomes more than 1. Yes? But just
one of them should be smaller than 1, right?
But just look at this. This is e to the power I something.
Yeah.
So this belongs
Complex.
no
It's minus.
to the circumference
Not circle.
Okay.
of unit 1.
This, you mean?
Yes. Every number that can be written in this form belongs in this here.
Same area. Yeah. Right.
If you put here r, then this is r, and this should be r and r. Yes, the r is the radius. Yes, but here, if we just took this number, we know that this is in this yes. So this point, the absolute value of this point doesn't affect us. Maximum is going to be 1. Well, no, maximum no, is going to be 1, literally, because it's the yes. So this implies that what we want is this to be smaller or equal than 1. Yes, but in the end, if psi is 3, then 3 to the power n is going to be get bigger and bigger and bigger. So basically, this, what we want is that psi is smaller or equal than 1. Yeah. And okay. Now I'm going to say, yep.
This one.
ما في example
Yes.
يوضح.
شوي
okay.
Yeah.
You mean okay. You mean
Yeah,
this one is smaller than 1, right?
No, it's 1. Basically, it's
Is 1, and this
Yeah.
this should be smaller than 1.
Yeah. Okay. Now, here, if we take Wjn to be what we did here, yes, if we substitute, yes, and here we want this solution, yeah, we take this as solution. So we go to the, we apply the FTC scheme, yes, and we just basically just plug this solution into our scheme. Yes, and then because we can cancel a lot of psi m's and x I w j, at the end we have that psi is this bit. Yes, if you just, I'm not going to show it because it's just like algebra.
What's this? That sign? What's it mean? W,
Sorry?
This sign.
This is this a constant in our case. Yes.
In our case.
In our case, let me check.
I think
in
all
our-
of this.
Yeah, no, here. In our case, we have yeah, sorry. In our case, it's I, J. So X, I, W.
E bar,
X.
E bar,
Yeah, so
I,
W. I'm just going to put it here. W in the nodes
equal
is, you have IJ, so it's pi k x.
like X.
Mm.
Yes?
Yeah.
Okay. Yes. And then again, from this, we have minus 1, 1 minus 4 times r sine square of W. I'm just going W halves minus 1. Yes, we
Then
have
enter.
this again.
Ah.
And
ما
as
عليك ممكن
we've seen
نحطها
here,
بالمدارس.
we had this kind of the same lambda, yeah, just differently in the middle here.
Mhm.
Yes, so if you, this is also like trivial, and the other part also, if you just compute it, you will end up with sine square 1 over 2
قاعد
omega.
تسهل عجل صح.
And sine goes from 0 to 1. If it goes to 0, this is going bigger, 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 bigger.
I'm very
And if it goes to 1, this goes to 1/2.
Mhm.
Yes, so the minimum, yes, it holds at 1/2. So you want r smaller or equal than 1/2. Yes,
According to the previous one, according to this one.
yes. So if we want this method to converge, we
Mhm.
need r
R
smaller
less than.
or equal than 1/2, which is the same
Here.
Okay.
as we had here, but this case is a more general case. Yes, it doesn't depend on the eigenvalues.
Not depends on eigenvalue.
No. Yes, and the eigenvalues are obtained if we have this formula, and this formula only is going to like be obtained in the parabolic case, not in the hyperbolic.
Parabolic, hyperbolic, high.
Yes.
What's mean hyperbolic and bible in numerical?
Hyperbolic and parabolic.
قطعة مكافئة أوريك إياها.
Yeah, I know the meaning like this and this.
Yeah,
But
basically.
what's meaning in numerical?
The solution, the form of the solution.
In our case.
Like you'll see it in PDEs.
Yeah.
You'll see why the formula and why is it called
I
parabolic.
think we take it.
You take it
I
back.
think it's some
Formula like less than one. I
Yeah.
think.
0.
No.
Huh? Distinguish.
A
Distinguish.
square
root. Distinguish root.
minus
Mm.
BC,
Like this.
Yeah.
and should be I think
Yeah,
smaller
but no,
than
but
If it's
I mean that
like-
the name.
This is abelic.
If this happens, you have I don't have it.
هذا hyperbolic.
I don't
It is-
exactly remember, but I know that if
Which
this
one
happens
equals 0?
and then it's called a parabolic, why is it called a parabolic? Because the formula of the solution it's like a parabolic parabola.
Mhm.
And the other form is like an hyperbola.
I will just let Muhammad just what is the question we started. شو رأيك بالسؤال بس هنا أوريك إيش معنى hyperbolic. What is the number one? This. أحطها بواحد. هذه أحطها باثنين. تعوض في المعادلة هنا. طلع لك parabolic ولا hyperbolic. فهمت علي؟
Yeah.
Or like if you can like this one.
This
yes,
one.
It's kind of t is equal
One.
to x squared. Yes. So that's why these are like a parabolic.
Like this one, right? This is
Mm.
because it's
Yeah.
parabolic.
No, this is equation
It's
equation.
like it's normally is by just look at this
Mhm.
and kind of do like this, and then this is the formula of a parabola. And then if you look at the hyperbolic and if you look at the elliptic, I don't remember exactly. When we go there, we'll see.
Okay.
Can-
We just like because it's has you have this relation. 1g equals 2 x's, and basically this is our normal formula for the parabola. That's why it's called this one is a parabolic one because this relationship is like a parabolic one.
Okay.
Yeah. Okay.
خلاص.
So again, yes, we end up with the same results, but this one is going to be a better method.
It's called about. What is the name? It's
Fourier.
Fourier.
And why is it called Fourier?
Yeah.
Because this sum that goes from minus j to j, this is called the Fourier expansion of u. Have you done Fourier analysis?
What's analysis?
Fourier analysis.
Real
What's
analysis.
Fourier analysis?
Okay, no.
حل حقيقي.
Well,
I
don't
need
worry.
real analysis.
Yeah.
I
So
need
for-
real analysis.
No, then Fourier is another one. It doesn't really matter. You don't have to know it. But like,
You memorize this theorem, that's it.
is it called Fourier because this is the how is it called? Like, what does it say here?
الله
Yeah,
يبارك. بس
basically
مرة
because
بعدين.
you write u as
That's all.
you know that
It was
we can write u as a with a Taylor series.
Yeah.
So we can write u as a Fourier series, and this is basically
Fourier?
Fourier.
Four.
It's like formula.
I'll
No,
try reading
formula.
So it's just like-
Fourier series.
Yes. So you can write u with Taylor, and you have like approximation of u,
Like
but
as
you can
usual.
also write u with a Fourier,
We haven't
and then you
studied
have
Fourier.
another approximations of u.
We haven't studied.
Yeah.
I think this.
Okay, don't worry.
We know Taylor.
This didn't arrive to Saudi Arabia yet.
It's just like remember that
We bring you to-
you can approximate a function differently.
Yeah.
Yes.
Have you finished?
We are with this, yeah.